Hello guys, my name is Lo Junyong Kevin, and today I'll be presenting to you guys my CS5230 project on quantum computation. So let us first start by asking, what is quantum computation? Quantum computation is a multidisciplinary field applying concepts of quantum mechanics to solve complex problems faster than on classical computers. As we may have been aware of, classical computers are very constrained in solving certain problems. There's a class of problems known as the NP-complete problems, in which no known efficient algorithms are able to solve them. For example, for the set problem, we do not have a polynomial algorithm to solve it yet. And for example, for the traveling salesman problem as well, another NP-complete problem, we are currently not able to solve these problems efficiently. It is the hopes of the quantum computation that is able to solve these problems much faster, perhaps exponentially faster than the classical computers. And the quantum computers, basically they work based on the fact that while classical computers work on bits, which is basically zeros and ones as we know, quantum computers work on qubits, which is actually 0 and 1 and a superposition of 0 and 1s. And I'm going to discuss about what the qubits will entail later on. Anyways, quantum computers make use of a lot of fascinating and cool concepts such as superposition, quantum Fourier transform, entanglement, and quantum interference. In all, it's actually a very fascinating field, but it's still yet rudimentary because it's still the quantum computers are still not fully developed yet. Later on, so the outline of this lecture, right, I'm going to discuss later on I'm going to discuss about the quantum gates, about how they can be visualized using the Bloch sphere. I'm also going to discuss on certain quantum algorithms, and then I'll also be introducing the class of BQP, the bounded quantum polynomial time, and I'll also be introducing to you the limits of quantum computing. And hopefully at the end of this presentation, you guys will have a much better appreciation and interest in quantum computation. So what is a quantum computer? A quantum computer actually is actually stored in this very cold environment, right, close to absolute zero. And this is because, right, because the qubits, right, they are actually very sensitive, and the quantum state is very fragile. So they need to be stored as close to a very low temperature as possible, and that's why they are put inside supercooled fridges to prevent the decoherence effects, which can have an effect on the superposition. Like it can cause qubits to tumble out of superposition. And since quantum algorithms rely heavily on quantum superposition, the decoherence effect should be prevented or minimized. So what is a qubit? As we know, for circuits, we have bits, right, which is 0 and 1. So while the bits make up the circuits, the qubit makes up quantum circuits, right? And the qubit is actually the basic unit of quantum information. And like the bits is useless without gates, quantum circuits as well will operate on these quantum gates, which we'll discuss later on. Anyways, qubits is basically this very tiny subatomic particles, such as electrons or protons. And we encode them in 0 and 1, the spin of the electron. So the qubits take on the values of 0 and 1 and a superposition of 0 and 1, which means that the electron can exist in both 0 and 1. It means that the qubit can exist simultaneously as both 0 and 1. And we'll discuss in a bit how this makes quantum algorithms, this forms the basis of quantum algorithms and make quantum algorithms such as the Shor's and Grover search algorithm so fast as compared to the classical algorithms. Moving on, now these are the three principles of quantum computing. The first is superposition, the second is entanglement, and the third is decoherence. Superposition is actually the ability to exist simultaneously in multiple states. Let me give you a real-world example of superposition. So, for example, the mathematical equation x squared equals 4, right? We can have two roots of the equation, x equals 2 and x equals negative 2. We say that these two roots are simultaneously the solutions of the mathematical equation x squared equals 4. Another intuitive example of what superposition entails is when we spin a coin. As we know, when we toss a coin, the coin lands head or tails, right? There's only which we can encode head as 1 and tails is 0. But when the coin is spinning, the coin is simultaneously both heads and zeros. And therefore, this is like a superposition. And yeah, and water waves also collides and can become superimposed with each other. Anyway, superposition helps quantum algorithms become very fast because it allows a vast amount of outcomes to be evaluated simultaneously. But the final result is only derived when the quantum state collapses to either 0 or 1. Moving on, we'll discuss about entanglement. Entanglement is actually the concept in which quantum states, regardless of their distance, so if two particles are entangled with each other, right, then their measurements and their behavior will be dependent on one another. For example, if we are going to the KFC, right, or McDonald's, if we buy one packet of French fries, another packet of chicken wings, if one packet contains the chicken wings, we can infer that the other packet must contain the French fries because we only have the chicken wing and the French fries. So the information in each packet is actually dependent on one another. And so, for example, if particles are entangled, if the total spin is 0, and if one particle is found to have a clockwise spin, then the other particle has to have an anti-clockwise spin such that the total spin can be 0. So yeah, because so that both particles, right, can have a total spin of 0 at the end. So one have to have a spin balancing that of the other particle. So this is what entanglement entails. So decoherence now. As we talked about earlier on, the quantum state is extremely fragile. This means that slight changes in temperature will cause drastic impacts on the state of the quantum computers by preventing the qubits to have this fascinating superposition phenomena. So that's why the quantum computers, right, let me reiterate, they have to be kept in very cold temperatures close to absolute 0. And we'll discuss later on why the decoherence effects is actually very big impediment for the quantum computers. Moving on, we'll talk about quantum weirdness, specifically the two-slit experiment. So basically, the two-slit experiment, right, it actually illustrates superposition, that the electrons can be in multiple states and locations simultaneously. This may actually go against our intuitive understanding of the macro world, because in the world we live in, right, as we know that humans, right, we exist in one particular place at one time. But it turns out for very, very small particles, right, our intuition doesn't let us understand this, doesn't really fit into these quantum particles, these subatomic particles. So basically in the quantum world, right, the particles can exist in multiple states and locations simultaneously. So this is the double slit experiment where there is a photon source shining or like emitting rate of electron at a rate of 1 electron per second or 1 photon per second, right? Then it's emitting into this wall with slits, which means there are openings, right? And for example, in the leftmost diagram, right, we cover the downmost slit. So photons are able to pass through the opening or the slit in the uppermost slit, and this is the pattern formed, right, on the array of detectors here. So these are actually called the array of detectors. So this is the pattern formed for the leftmost diagram, and likewise for the rightmost diagram, with the uppermost slit being covered, photons will be able to pass through the downward slit, and the pattern is actually very similar to the one on the left. So we have this wave with this phenomenon, right? And now the thing is that when we have when we uncover both of when we do not cover the slits, right, we observe that this pattern right now is actually a bit against what we expect or what we would intuitively be able to understand. So we would expect that the number of that a pattern for when we do not cover any of the slit to be actually this pattern plus that of this, right? But however, it turns out that at some detectors, right, when we do not cover any of the slits, right, we actually experience lesser electrons than when we cover the slits, which is actually very surprising. So actually the double slit experiment kind of illustrates to us that the electrons must have somehow instantaneously explored all the possible paths, right? And like when the slits are open, such that it's dependent on the number of slits. Okay, so right now I'll be explaining to you guys the Shaw's algorithm. Shaw's algorithm is actually used to factorize integers. So as you know that if the integer is very large, for a classical computer to factorize it, it's going to take the classical computer very long, right? Depending on how large the integer is, it is even possible for the classical computer to take thousands of years to factorize the integer. Imagine we have an integer with like 1,000 digits or etc., right? So as you know that, for example, for like a lot of encryption, like for example the RSA, all this relies on like a lot of like very long integers to decrypt it. So Shaw's algorithm, right, is actually very useful in this aspect to decrypt to factorize very large integers. So specifically, Shaw's algorithm uses the principles that I mentioned earlier on, like quantum superposition, also uses another principle called quantum Fourier transform. Right. So quantum computers, right, will very quickly factorize out factorize out the integers. It's also useful to note that classical computers can perform Shaw's algorithm, albeit it's actually going to be run a lot slower than the Shaw's than performing on the quantum computer. For classical computers, actually, right, the best way to factorize integers is not using the quantum algorithms, but rather using the algorithms suited for the classical computers, like for example the sieve method. So anyway, the quantum computers, right, they are still at a very rudimentary level, so there's no need to worry about all this like decryption stuff yet. Yeah, there's no immediate risk to encryption just yet. Quantum computers as of now will not be able to factorize out integers that are very, very large. Yeah, so they are still at a rudimentary level. Now I'm going to outline what Shaw's algorithm is. So basically, basically for the integer, right, the very large integer, we want to guess a number that may or may not share a factor with n, right? And actually, we can check whether a number shares a factor with n by using the uSlits algorithm, right? So specifically, if the GCD between two numbers is 1, that means they are co-prime, which means that they do not share a factor. If the GCD on the other hand is greater than 1, that means the two numbers share a common factor. So if the GCD is not 1, right, that means we found a common factor. But however, if it doesn't, right, then this is where Shaw's algorithm comes in to turn the guess into a better guess, right? So specifically, Shaw's algorithm states that for every guess, right, that does not share a factor with n, g to the power of p over 2 plus 1 and g to the power of p over 2 minus 1 are better guesses. However, how do we find the p? As you know, this p is arbitrary, right? And so for classical computers, right, to calculate p, it can be very challenging to calculate p because it may need to like go through many operations. However, for the quantum computers, right, they actually need to go through just like fewer operations because of the quantum superposition, right? So they basically, so this is what I'm going to explain later on. Anyways, so yeah, so this is the general outline of the algorithm written in like more formal notation. So like for example, the GCD greater than 1, that means they share common factors like what we mentioned earlier on. And if they don't share common factors, then based on this mathematical theorem, right, a to the power of p, right, that means if you multiply a just enough times, by so like a multiplied by a multiplied by a p times, will be equals into sum m multiplied by b plus 1. So let's illustrate using an example, right? So let's illustrate using the two numbers 7 and 15. So clearly, 7 to the power of 4 is equals to 160 multiplied by 15 plus 1. Right? We can always verify this, right? So actually, we mentioned just now about the a, right? Yeah, so we can actually bring the 1 over, so it will become a to the power of p minus 1 equals to m and b, and then we can kind of like factorize out into this way. Remember the a squared minus b squared equals a plus b multiplied by a minus b, that concept, and we factorize it out into this form. The reason why we factorize out into this form is so that like we can find the two factors earlier on. Yeah, we'll see just in a bit. So basically with the quantum superposition, right, like you can simultaneously calculate a bunch of possible answers for a single input. You can calculate all these many p at once, like using a quantum superposition. And then we can also get all the wrong answers to destructively interfere with each other. Like for example, if we know a to the power, if we know p is like whatever number is wrong, and then and then we just get all these to destructively interfere with one another, and so we send in the superposition of all possible powers that the guess could be raised. That means in this case the p value, and then we also send in a superposition of how much bigger each of these powers are than a multiple of n, because we just want it to be 1 greater in the end, right? So to guess p is very slow on classical computers, like what we mentioned earlier on, because classical computers need to perform many operations to guess the p. But because of the quantum superposition, we are able to calculate very fast. Yes, and then later on they just put the superposition into the quantum Fourier transform. So this is an example of Shaw algorithm using n equals 15 and g equals 4. That means the initial guess is 4 and the integer to factorize is 15. As evidently we can see that 4 is obviously not a multiple of 15 because the GCD of 4 and 15, right, is going to be 1. That means they are not a factor. 4 is not a factor of 15. So we repeatedly multiply so step 1 states that we repeatedly multiply previous remainder initialized to 1 with g at mod n. So my 1 multiplied by 4 mod 15 is just 4 mod 15, which is going to be 4, And then we take this result here, we put it right here, and we multiply it again by g and mod n, right? So it's 4 multiplied by 4 mod 15, which is just 16 mod 15, which is 1. And evidently the number of steps is 2. So actually if the number of steps is actually going to be odd, right, then we need to repeat the algorithm, because p is defined to be the remainder in r over 2 steps. But if r is odd, let's say r is 3, right, then how are we going to perform it in the 1.5 steps? So if r is odd, we basically need to like guess another number. Let's say we can guess, let's say if we have two numbers, right, like that, yeah, let's say we guess like a number x that is wrong, and then we can take another guess again to keep on repeating until we get an even number of steps. Now p is the remainder in the r over 2 steps. Recall that r is 2, so the remainder in the first step is just 4. Yeah, so as you can see, right, like for the classical computers, like you may need to keep on repeating this algorithm again and again, which can make it slow. Anyways, step 3 states that we check if p plus 1 equals to n. So in this case, p is defined by r over 2, right? The remainder in r over 2 steps, so it's defined to be 4. 4 plus 1 is clearly not n, which is 15. So, but if p plus 1 equals n, right, which can occur sometimes, then we need to repeat the algorithm again. Anyways, we take the GCD of p plus 1 comma n, which is the GCD of 5 comma 15, which is just 5, since 5 is the greatest common divisor between 5 and 15. And then we also take the GCD of p minus 1 comma n, which is just 4 minus 1 comma n, which is 15. So the GCD of 3 comma 15 is going to be 3. And indeed 3 and 5 are the common factors of 15, right? Specifically 15 equals 3 multiplied by 5. Okay. So right now I want to explain to you another example for Shaw's algorithm. And this example is kind of a failed example to illustrate that sometimes you may need to repeat the algorithm. So if we remember previously, we didn't have to repeat the algorithm with n equals 15 and guess equals 4. But in this example right now, we'll show that we will need to repeat the algorithm. So here are the calculations I outlined. Firstly, we start off with 1. So 1 multiplied by 8 mod 27 is just 8. And then 64 mod 27 is 10, 80 mod 27, 26, so on and so forth. And we get 1 in the end. And notice that the number of steps is 6. So r will take on the value of 6, and p, which is the remainder in the r over 2 step, which is the third step, is going to be 26. And now notice that p plus 1 is equals 26 plus 1, right? So it's equals into n. P plus 1 is n. We have to repeat the algorithm. This means that our guess of 8 is actually not valid, and we need to repeat the algorithm again. Okay, so previously, as you recall, we did not need to repeat the algorithm because r is even and p plus 1 is not n. But in this case, p plus 1 is n, so we need to repeat. So just something to keep in mind. Okay, now we'll talk about bracket notation. So bracket notation, right, is actually the notation to represent quantum states in quantum mechanics. So we have the angle brackets and vertical bars. This is the vertical bar and this is the angle bracket. So this is how qubits are represented. So we have this. So I just outlined and showed these two examples of how 0 and 1 are represented. Now I want to talk about the Bloch sphere. So as you know that for qubits, right, they are actually encoded as in like the electron spinning around, right? So it actually sometimes can help, and it can be more intuitive to think about it as a sphere, right? So this illustration will come in helpful when we visit gates, right? Quantum gates, which will be what I'll be talking on shortly. Quantum gates. So if you recall in Boolean circuits, right, or circuits, is actually created by like gates, sources, gates, and the sink, right? So how the Boolean circuits act on bits, which is 0 and 1 basically, quantum gates acts on qubits. So basically qubits are useless if we do not have anything to compute in, right? So we need the gates, quantum gates, to compute it. So quantum gate is a rudimentary quantum circuit operating on a small number of qubits. It's a directed acyclic graph like the Boolean circuit with sources, sinks, and internal nodes denoting the gates. And it's denoted by 2x2, 4x4, 8x8 unitary matrix. And one thing that is quite interesting about quantum gates is that operations are reversible. As we know, that it may not be the case for classical circuits. So these are some examples of quantum gates. We'll be talking more about them later. The Hadamard gate is the one that will be used in the later algorithm as what we'll see. And these are basically the equations matrix and the notations of all these gates. Now the Hadamard gate, which is what we are going to talk on later, is actually the most, we are going to talk now, is the most frequently used in quantum gates. And then it basically helps to put the qubits into superposition. So basically most quantum algorithms, right, because they use superposition, in order to put the qubits in superposition, they need the Hadamard gate. So it's actually also called the H gate, and it's performed by bouncing microwaves off the qubits. So this is the Hadamard, the name of it, and then this is the representation, and this is the matrix. It's a 4x4, it's a 2x2 matrix represented in this way. Now we'll talk about the poly X gate. So later on we'll be seeing the poly X gate, the Y gate, and the Z gate. All of them are phase flip gates, and they only differ in how they cause the rotation about x-axis, which you can actually visualize using the Bloch sphere actually. So the poly X gate, right, is one that causes rotation around the x-axis by pi radians, and actually essentially it just performs a negation. So this is actually the representation of poly X gate, and this is actually the representation. So as you see, 0 is now negated to 1 and 1 is negated to 0. Now we'll talk about the poly Y gate. Like the poly X gate, right, it's a phase flip gate, but this time around, instead of causing rotation around the x-axis, poly Y gate causes rotation about the y-axis by pi radians. So this is the Bloch sphere actually, and then we will see that the arrows got reversed because it's rotated around the y-axis by pi radians, which is basically like just rotating by 180 degrees. This is before applying the Y gate, the poly Y gate, we have this, and after performing this, now the arrows get rotated by 180 degrees or pi radians. Now we'll talk about the poly Z gate. Similarly, it's a phase flip gate, and this time around causes rotation around the z-axis by pi radians. So this is the name, this is the representation, and this is actually the matrix. Now we'll talk about the C0 gate. The C0 gate flips the target qubit if and only if the control qubit is 1. So we have the target qubit and the control qubit, right? And it only flips if and only if the control qubit is 1. It flips the target qubit. Now look at the diagram. The diagram is here. As you can see, because the control qubit, right, is 0 here, therefore there is no change in the before and after. Now the target is 1, and therefore because the control is not 1, the control is 0, therefore these two rows are the same. This now the control is 1, so therefore it flips the target from 0 to 1, and this is 1 as well, so it flips the target from 1 to 0. So this is a C0 gate. Now this is the gate matrix for the C0 gate. Now I'll talk about Grover's algorithm. So Grover's algorithm is actually one of the quantum algorithms, right, that leverage on phase interference and superposition in addition to amplitude amplification to actually locate element to be searched. So unlike most quantum algorithms, right, as we know, most quantum algorithms provide exponential speed up in the time. But Grover's algorithm, unfortunately, is not able to do so. It's able to only perform a quadratic speed up. So the thing is that the problem about the unstructured search, right, in which Grover's algorithm can be applied to, is actually one in which we want to search an unstructured database, right, for a winner in this case. And then, as you know, the classical computer has to go through everything, and it needs to at least go through half of it to have a 50% chance of finding the winner. But however, the Grover's algorithm is able to do this in O root n, which is actually a bit faster. So classical computers are only able to perform it in linear time, but quantum computer runs it in O root n time. The Grover's algorithm can be used for estimating the mean and median of a set of numbers. There's some applications, and it can also solve NP-complete problems relatively fast, but still an exponential amount of time, like the set problem, by performing exhaustive searches. So basically, the set problem as we know it, our current algorithm, right, is actually going to be an exponential algorithm. And because the Grover's algorithm is like root of an exponential, it's actually still going to be an exponential time. So Grover's algorithm, the key point is that it only provides a quadratic speed up. Okay, so right now we'll be talking about the complexity class BQP for bounded quantum polynomial time. So basically BQP is the class of decision problems solvable by a quantum computer in polynomial time and erring at most 1/3 probability. Actually, 1/3 is kind of arbitrary. We just want any number that is, like, we just want it to be accurate more than half the time. That means more than half. That means better than a coin flip result, right? More than just random chance. So here's one thing to note. The second thing to note is that it means that if a problem is in the language, right, then a BQP algorithm should accept that problem, right, at least 2/3 of the time. It should accept the problem in a high probability. Whereas if the problem is not in the language, then it should reject it in at most 1/3 of the time. Yeah, and if the problem is not in the language, then it should wrongfully or erroneously accept it in 1/3 of the time, and it should reject in 2/3, at least 2/3 of the time. So the BQP algorithm, right, can be kind of like reduced. The error probability of the BQP algorithm can be reduced by repeatedly performing the algorithm multiple times. And then each time, and then after you perform it, like let's say n times, you take the majority answer, and this will kind of reduce the error probability and make the error probability as close as to 0 as possible. So BQP can also be thought in terms of a quantum Turing machine. Specifically, the quantum Turing machine should accept any problem in the language at least 2/3 of the time and reject 1/3 of the time. So previously we kind of discussed two BQP algorithms. One of them is actually going to be the Shor's algorithm. If we recall correctly, like Shor's algorithm factorizes out integers, factorizes out a large integer, and then the Grover's search algorithm for unstructured search in databases. Okay. Moving on, this is the BQP diagram. It's kind of hierarchical in structure. We kind of see that from this diagram that BQP contains the complexity classes BPP, RP, ZPP, P, and CoRP. And important to note that it's contained within the P space. Okay, so yeah, we'll kind of explain like the theorems in a bit. There's quite a number of theorems to explain for this. So the first theorem is BQP superscript of BQP equals BQP. This means, right, that what this theorem is trying to say is that if we have a BQP algorithm and then we have a BQP oracle solving that problem, or as a subroutine to solve that BQP algorithm, it's actually no more powerful, right, than ordinary BQP algorithm. And the way to solve this is that we observe that BQP is actually a polynomial algorithm. Based on its definition, it's solvable by a quantum algorithm or quantum computer in polynomial time. So it's actually a polynomial algorithm, and like a polynomial, like P, like a polynomial algorithm having a polynomial algorithm as an oracle, right, it should be no more powerful than a polynomial algorithm. So that should explain this theorem. Now moving on, we're going to find the relationship between BQP and P. So from this diagram, we can see that P is clearly a subclass in BPP, right, and BQP. So the reason behind this is that the classical circuit can be simulated by a quantum circuit. So basically, quantum algorithms and quantum circuits, right, they're always at least as powerful as the classical circuit. Right, that's an interesting observation. So, for example, right, the NAND gate is universal for classical circuits because you can use the NAND gate to simulate all the other gates like the OR and NOT gate. For the quantum circuit, right, or the quantum context, the gates, the Toffoli gate and the Hadamard gate are the universal gates, right? That means they can simulate all the other gates. So the Toffoli gate is one, right, in which if there are two, if the first and second bit is 1, then the third bit would be inverted. And in all other cases, the third bit stays the same. Because we are only interested in the third bit, right, we can define a Toffoli prime, which actually just return us the third bit. So for example, Toffoli prime of 1, 1, comma x will just return the negation of x because 1 and 1, because the first and second bits are 1. Therefore, if we apply Toffoli gate, it should negate the third result, and Toffoli prime is just producing the third result. So, not x, right? That means, right, in the classical circuit, we obviously have the NOT gate. So, applying NOT to x, you should negate the x, right? And this is negated because the first and second bits are 1, and therefore, the Toffoli gate would negate x to be negation of x. And the Toffoli prime will just return the third bit. So you get x prime, or you get the negation of x. And n of a comma b, right? So you know that n of two numbers 1, like let's say n of like 1 and 1 should give us 1, n of 1 and anything that is not 1 should give us 0, and n of 0 should give us, n of 2 0 should give us 0. So if a and b are 1, and then it will negate the last bit to be 0. I mean, you'll negate the third bit of 0 to 1. So therefore, and the Toffoli prime will just return 1. And if it's 1 and 0, then in all other cases, right, that is not, the a and b do not take on the value of 1 each. It will not negate, and the result will be 0. So that is what it means. And the OR is slightly more complicated, but it's actually using the De Morgan's law of a combination of AND and NOTs, not an AND gate, and we kind of proved already that each of the AND and NOT gates can be simulated by the Toffoli gate. So this actually shows us that the Toffoli gate, right, can actually simulate all the gates in the classical circuits. Okay, by the way, the NAND, right, just now I forgot to explain. NAND is actually like you AND 2 bits together and take the negation of it. For example, the NAND of 1 and 1 is going to be 0 because the AND of 1 and 1 is 1, and we take the negation of 1 to be 0. Likewise, the NAND of 1 and 0 is going to be the AND of 1 and 0 first, which is going to be 0, and then you negate, the answer is 1. So the NAND of 1 and 0 is kind of 1. Now, moving on, we'll examine the relationship between BPP and BQP. So BPP is contained within BQP, right? You see, from this diagram. And why is this the case? Because we kind of already know that quantum computers, right, can efficiently solve any problems that are efficiently solvable by the probabilistic Turing machines. So probabilistic Turing machines, they are kind of like the Turing machines for the BPP algorithms. And quantum computers will always do better, better than them, because it uses, instead of just 1s and 0s, right, it kind of also uses superposition of 1 and 0. So that's the intuition behind why BPP is contained in BQP, which means that any problem that can be solved in BPP can also be solved in BQP. Okay, moving on. Now we'll talk about the relationship between BQP and P. Okay, so actually this one should be, yeah. So just now I forgot to explain also that like to get the bits, right, to get the bits for the classical circuits, we can use the Hadamard gate. Yeah, so that's something to keep in mind. The relationship between BQP and P space. So as we kind of explained earlier on why the Toffoli and Hadamard gates are the universal set of gates for quantum circuits, because the Toffoli gate can perform the functionality of the AND, OR, and NOT gate, and the Hadamard gate can be used to like put the bits into superposition and kind of generate random bits. So we can use all of them together to generate all the sets of like classical gates, or the gates in classical circuits, and we can also generate random bits using the Hadamard gate. So basically the Toffoli gate acts on 3 bits at a time by definition, and there will be 2 to the power of 3 equals 8 recursive calls. And because we reuse the space in each recursive computation, we find that BQP is contained in P space. We use polynomial amount of space only. Right, so to illustrate, P is within BPP, and P is within BQP, and BPP is within PQP, and BQP is within P space. So these are the theorems for that. Also BQP, right, and EXP, right, they are kind of related. So how are they related? BQP is actually a subset equals into EXP. The reason being is that BQP is in P space from the earlier proof. As in the previous proof, right? We kind of already explained why BQP is contained within P space. And then we also know, right, the fact that P space is contained in EXP. So specifically, P space refers to like all the polynomial amount of space, and EXP refers to the problems that can be solved using a deterministic Turing machine in exponential time. So anything you can solve in a polynomial amount of space, you can solve it in exponential amount of time. That is a well-known fact. And combining these results together, we can find BQP in EXP. Because BQP is in P space, which is in EXP. So therefore, by transitivity, we kind of say that BQP is in EXP. So any problem in BQP can be solved deterministically by a Turing machine in exponential amount of time. Now we'll talk about QMA. So basically, QMA, right, is if we recall, it's actually the quantum analog of MA. And if we recall, there are 2 fictitious agents, right, called Merlin and Arthur, whereby Arthur is the verifier and Merlin is the prover. So the prover has unbounded computational power, and basically the prover is supposed to convince the verifier of the proof at hand. So basically MA is a set of languages, right, for which you have a Turing machine M and polynomial size certificate C. And then if X in L, A, X, C accepts with high probability, we can define it arbitrarily as 2/3 or whatever. And if X not in L, it accepts with low probability. So QMA is the quantum analog of MA. We can just quantize the verifier algorithm and certificate. So we know that in the MA algorithms, right, the verifier is you can think of it like a BPP machine, right? Because it uses kind of like the BPP machine, like some BPP algorithms. Whereas the QMA is not using BPP algorithms, it's using the quantum analog of it, right? So it's the BQP algorithms to verify, right? And then QMAK, right, is defined to be the language for which there are K Merlins. So now there are K provers, right, each sending the verifier a quantum proof. Now we talk about quantum interactive polynomial time, or QIP. So it's the quantum analog of the complexity class IP. Right, where the prover and the verifier communicates in a quantum channel, and the verifier can perform quantum computation. So recall that IP is actually the protocol in which the verifier and the prover communicates, right? And then they communicate, and in the end the verifier needs to decide whether to accept or not the proof of the prover. So QIPK is a set of languages with quantum interactive proof protocols of length k. And basically QIP is contained in p space in EXP, and QIP equals IP equals p space. Okay, I want to now talk about the open questions, right? So some questions, basically, we currently do not have the answers to them. So the first question is NP contained in BQP? So that is like for any problem in NP, right? Can we always have a BQP algorithm to solve it? Like in polynomial time. And there's a lot of reasons to believe otherwise, a lot of theories believe otherwise. The reason is because for example, we talk about the Grover search algorithm, right? Is known to some BQP algorithms just not able to solve those NP complete problems efficiently. Basically, NP complete problems, it's not believed that these NP complete problems will have polynomial solution even if we manage to use a quantum computer. The second question is, could BQP contain problems outside of NP? Because the class of BQP is so big, could they contain problems outside of NP? And also, there's actually the containment of BPP in BQP. Are they strict? It's actually, for example, the diagram that I illustrated here, right? You see, it's actually possible that if BPP is inside BQP, right? Or for the matter what, if P is inside P space, for the matter, maybe there is no, you see this area over here, and maybe there is no overlapping, and everything is just one class. So we don't have a proof yet, but I think likely that we do not have a proof yet. But the thing is that factoring, right, which is believed to be in BQP, right, that means because factoring, remember, we have the Shor's algorithm is in BQP, but it's not in BPP, and we don't believe we can ever solve factoring in polynomial time. But however, we do not have a proof of this. And then also about P equals P space. Basically, if P equals P space, that means if it collapses all to polynomial amount of time, this means that quantum computers, right, offer no computational advantage over classical computers. Which means that all these factoring problems, right, we'll eventually find a polynomial algorithm to solve them. That's if P equals P space. So quite interesting, but so far we have no real proof of supporting or against these theories. Okay, right now we'll be talking about the limits of quantum computing. So basically, we know that quantum computers, right, they are very sensitive. and they need to be stored in very cold temperatures, in absolute zero, like near to absolute zero temperatures, because the quantum state is very fragile, and decoherence effects will kind of minimize or prevent superposition. And most quantum algorithms uses superposition, so it's actually very difficult to build because of how sensitive the quantum state is and how sensitive quantum computers are to heat and noise. And also the thing is that we kind of seen earlier on Shaw's algorithm. Shaw's algorithm is a factoring algorithm, and what happens, right, if and we are not able to ascertain whether whether such quantum algorithms is able to break encryption schemes in future. If so, then the whole internet will be in danger, right? So before actually advancing in quantum research, we kind of also need to enhance our encryption scheme such that these encryption schemes are less prone to quantum computing attacks. Currently, quantum computing is still in a very rudimentary phase, so it's actually an open question also whether or not we can actually be able to build quantum computers that are so advanced. But it's also worth noting that IBM and Google are expending a huge amount of money, like billions of dollars, trying to build quantum computers because of their extreme speed, right? It's so much faster than the classical computers because of their ability to do quantum superposition. So there's also basically quantum computers are very difficult to build, and they can also be very expensive. So right now, okay, it takes a long time to build as well. So right now, the state of our quantum computers are very rudimentary. Because of all the weird properties of quantum physics and quantum mechanics, we are also not able to ascertain whether or not such quantum computers can ever be built or ever to be advanced enough. So now I'm going to wrap up the conclusion. So as we know that the quantum world is very different from the macro world. The things in the macro world, for example, like our laptops, even us as a whole, our rooms, they do not exist in superposition, right? They always have a definite property, meaning that they're always at a specific location at one point in time. However, the quantum mechanics says that these subatomic particles, that means when things get to very, very, very astonishingly small particles, they kind of disobey Newtonian or classical physics. And we cannot really use our understanding of the macro world and our physics that we kind of observe as a day-to-day basis, namely Newtonian physics, to model the quantum world. Quantum particles basically behave in very strange ways. As illustrated in the two-slit experiment, the electrons actually, they do not have a definite property. They are actually in multiple places at any one point in time. And also the electrons, and also subatomic particles can be entangled with one another irrespective of distance. Actually, many people strive to understand quantum mechanics, but I think Richard Feynman also said that nobody really understands quantum mechanics, and that is also one of the limitations of quantum computing, and that is the reason why we kind of need to research more into it. If quantum computing is successful, then it will actually be very good way for humanity, because now many NP-complete problems can be solved very fast, and it's basically going to be very fascinating, right? But yeah, and quantum computers, they are basically, with their potential, it kind of will benefit humanity a lot, especially for a lot of tech companies where they want to compute results very fast. So the second thing is that also that we want to also say that quantum algorithms, right, they are typically faster than the classical computers because of the ability of the quantum superposition effect, right? Such that the qubits is actually able to store more information than the bits because of being able to exist simultaneously as 0 and 1. and not just 0 and 1. So the quantum computers also, they are very sensitive. Quantum state is very fragile. They need to be stored in very cold temperatures. And quantum algorithms will include, like there are many quantum algorithms and also algorithms that are not really discussed here because they are not very practical as of today, like Simon's algorithm. But we kind of discussed the Shor's and the Grover search algorithm. The Shor's algorithm, right, recall that it runs in linear time with respect to the number of bits of the integer. So for example, for any given integer n, it will run in O log n time because the number of bits will be log n. But in this case, we just say that assume that the number of bits is n. So Shor's algorithm run in On is used to factorize out very large integers. Used to factorize out very large integers, and it makes use of quantum superposition and quantum Fourier transform. And basically because of the ability to like simulate many powers of the p, right? Many p possible values at once, right? Rather than the classical computer need to do it like sequentially, quantum computers, right, using the Shor's algorithm will factorize out large integers exponentially faster than the best classical algorithm to factor an integer. So that is Shor's algorithm. We also talk about the Grover search algorithm, which is currently merely quadratically faster than the known classical algorithm. Recall the Grover search algorithm is used for unstructured search, where we want to search a winner or like a specific element or even multiple elements within a set, and also can be used to find mean and medians very efficiently. So Grover search algorithm is merely quadratically faster. It's also used as a brute force to solve like many NP-complete problems. And also lastly, right, there are many quantum analogs of classical models of computation. So for example, like in the classical models of computation, we see IP, right, interactive proofs. So there's also a quantum version of it. Basically the quantum version, like instead of the verifier being a BPP machine, the verifier can be a BQP machine, and where there's a complexity class MA. For Merlin and Arthur, there's a quantum analog which is QMA, which we discussed earlier on, and so on and so forth. There's also QAM, etc., etc. So all in all, quantum computing is actually a very fascinating field. It's a very fascinating field, and quantum mechanics is, and we don't really understand the full details of quantum mechanics just yet. And we hope that with more and more, as time progresses, we kind of like will be able to build the quantum computers. It's also an open question as to whether or not such quantum computers will ever be built, or rather they are already built, but whether or not they can be built to be meaningful enough. Okay, and we also discussed some other open questions like whether or not the complexity class of BQP could potentially have problems outside of NP. And we also discussed whether or not P can be equals to P space, and whether or not like the containment of the classes need to be strict or not. For example, we know that BPP is a subset of BQP because quantum computers are definitely as powerful as the classical computers, since quantum computers operate on qubits, which is actually at least as powerful as the bits that the classical computers operate on. And so like if P equals P space, then actually quantum computers will not be very significant because quantum computation will no longer confer any computational advantage over classical algorithms. So many companies actually have been expending a lot of money, billions of dollars, right, into quantum computing research. For example, the companies like Google and IBM are expending a lot of money like on quantum computing research. As can be seen, quantum computers, right, like can have the potential to solve problems very fast, and actually can also give us deeper insight into even classical computer algorithms. With that being said, quantum mechanics is actually a fascinating field, and hopefully quantum computers can advance even more, because right now it's still at a very rudimentary state, and we kind of already know that quantum computers have a lot of potential. Okay, with that being said, I think this will mark the conclusion of the quantum computation project. It has been a very fun project to do, and it helped me understand quantum computation a lot better. Okay, thank you. Goodbye.